The European Union aims to move towards a low-carbon economy, contribute to the mitigation of climate change, following its commitments with the Paris Agreement. Under this context, the EU 2030 Climate and Energy Framework presents us key targets: cuts in greenhouse gas emissions, increase on share for renewable energy, and improvement on energy efficiency. The buildings should play an important role in this transition, as in the EU they consume 30% of the energy and are responsible of 36% of the CO2 emissions. The goal is to move to a nearly zero energy building scenario, which should present high efficiency and low energy consumption, mostly generated locally through renewable sources. Since it's more difficult to control when and how the energy is generated, demand response schemes are gaining a significant role within energy markets, shifting the energy needs to hours with high renewable production. Buildings can provide such stability to the grid, increasing or reducing their energy consumption based on global needs, supported by renewable systems, local energy storage, power-to-heat conversion, or through smart operation of appliances and equipment. Aggregating multiple buildings' demand enables the management of large amounts of energy needed for energy market balancing. In summary, demand response can contribute to the timely realization of EU 2030 policy objectives and the speedier transition toward a decarbonized energy system with active citizens, improved energy security, and reduced energy poverty. The challenge is to integrate demand response, enabling technologies into energy management systems that optimize energy consumption, production, and storage based on the needs of the different actors involved in the value chain. Holisder presents a DR optimization framework, bringing together a wide range of mature and proven technologies and integrates them in an open and interoperable framework, comprising in a fully-fledged suite of tools and apps for all major stakeholders. Holisder system architecture has been broken down to three main component groups: the global and local demand manager layer, to offer the necessary functionalities to the retailers and the aggregators, and implement DR schemes at building level to engage the end consumers. The visualization platform and end-user toolkit layer, consisting of a number of modules exposing user interfaces, web and mobile, to the end users of the platform. The interoperability and secure data management layer, to ensure technical and semantic interoperability across the DR value chain through the utilization of well-established open standards and protocols. Holisder ensures consumer empowerment and transformation into active market players through the deployment of a variety of implicit demand response schemes, both supported by innovative end-user applications to enable personalized informative billing, human-centric energy management, load scheduling and intelligent controls, self-consumption promotion and cost-effective storage, predictive maintenance, along with the context-aware automation. It also safeguards the reliability and stability of the energy networks through the deployment of explicit demand response schemes. Holisder framework is validated in 4 large-scale pilot sites located in Finland, UK, Greece and Serbia, which ensure complementary in terms of climate, building types and uses, VR market maturity, culture and demography. The pilot buildings require an upgrade on their level of smartness to enable the implementation of energy efficiency and demand response strategies and initiatives, which imply the deployment of hardware and software solutions. Greek pilot site is composed by 3 miscellaneous utilities, 2 office buildings and 25 residential dwellings across Athens. Reward-based occupant VR program. The first use case related to the Greek pilot site entitled the implementation of a recommendation service towards residential consumers for peak demand reduction and energy efficiency. Results show a reduction of 11.65% of average energy consumption, which translates to approximately 120 euros per user of annual savings. The second use case considered for the Greek pilot site revolved around a recommendation service for energy efficiency and energy waste reduction, targeting the office building employees and facility managers. This scenario will be implemented once employees currently on teleworking due to COVID-19 return to the office routines. The UK pilot is composed by diverse buildings from Kiwi VR, aggregators portfolio of clients in London with special focus on a large office building and a 3 buildings residential complex. The first use case of the UK pilot is related to the estimation of potential flexibility from large HVAC equipment installed in commercial buildings being a key factor for aggregators in order to build up their portfolios of assets, identify the most interesting assets and quantify feasibility of implementation. For this office building, with about 1 MW on chillers, it has been assessed a potential downwards flexibility amounts to 15 MWh, whilst the upwards flexibility to 42 MWh. It can be also deduced that the early revenue due to the cooling flexibility would be around 11,000 euros. In the case of residential complex, the main objective was to achieve energy peak demand reduction through a reward-based notification framework directed to the end users. Results show an average peak demand reduction of around 47% per event and user, while the average savings in each home was of 1.26 kWh per VR event. The Finnish building management cases led by Caverion were composed by 3 heterogeneous buildings, 1 shopping center, 1 multi-apartment building and 1 office building. The first validation scenario in this site carried out a reduction of power peaks and electricity consumption through the demand response based management of ventilation systems. Results show up to 30% of power consumption reduction, meaning around 300 euros of annual savings in the electricity bill for a medium building with centralized ventilation system. Secondly, it was analyzed how pilot's portfolio of buildings can contribute to grid stability, providing flexibility to solve voltage problems resulting from over or underproduction of renewable energy in the distribution network. Results show that buildings can provide 80% of their flexibility thanks to their thermal mass. Moreover, 70% of voltage problem could be solved by the effect of the flexibility. The Serbian pilot site is based on Beoleg, local district heating company's customers on the large Stepa Stepanovic residential neighborhood. The main objective of the use case was to provide decision support tools for VR in order to choose the more economic heating system between the available options, reducing therefore the energy cost of heating for residential occupants. Providing a dedicated smartphone app for consumers enable informative billing, energy efficiency awareness increase, and to provide them daily personalized VR recommendations. These recommendations had an acceptance rate of over 74%, and besides convenience benefits, the estimation is to provide each home about 45 euros of cost reduction per heating season. Holisder has an impact on the environment. great potential to contribute to the energy source saving, harmful gas emission reduction, raising of people awareness of self-control in energy consumption. Holisder project is coordinated by Technalia with the participation of another 12 companies and institutions from 9 European countries.